Well, we're going to talk about continuity. And as we explained, or as I explained in the previous video, continuity means if I can graph it without lifting my pencil, then it's continuous. But that would also indicate that there is discontinuity. And so we're going to look at the three types of discontinuity, which are infinite, jump, and removable. We'll take a look at those three types, and then we'll go into, in this lesson, a test for continuity. Now, in this test for continuity, we're not talking about whether the entire function or the graph of the entire function is continuous, but rather we're looking at a specific point, a specific x value, and is the graph continuous or not at that point. And then there is a continuous, or a continuity, I should say, a continuity test that we'll consider. And that'll kind of get us into limits, a little bit kind of drive you crazy. However, we're going to use our calculator. Our calculator is going to be our friend. And rather than do some of the tables and charts, we're going to allow the calculator to work for us. But we'll take a look as we here looking at both the types of discontinuity as well as the continuity test. Okay, so continuing to look at discontinuity, or continuity, I should say. That also leads us to the fact that there must be discontinuity if we're even raising the question. And here are three types. This is showing us three types of discontinuity. And so over here on the left, this is an example of where we have infinite discontinuity. In other words, this is never going to be continuous. And we can see from right here that, let's go right here, that at this point right here, where f is equal to c, and I cross through c, that our graphs are, this is the point at where discontinuity exists. And it would appear that it is always going to be discontinuous at that point. That would be infinite discontinuity. And that, in looking at that, so what causes infinite discontinuity? Well, that could be violation of one of our two, either or both of our two cardinal rules that we can't do, which is divide by 0 or take the square root of a negative number. That's going to give us infinite discontinuity. And you see an example of that here. In this one in the middle, we see an example of jump discontinuity. Now, this would tend to be a piecewise function, and we can see here that at this point C, right here, when x is equal to C, we've got discontinuity because obviously I can't graph those two without lifting my pen, and it jumps from here to here. That would be an example of jump discontinuity, and that is most often going to be associated with piecewise functions. Okay. Now, the third one, we got removable discontinuity. And we can see evidence of that. Here's x is equal to c. And we've got a hole, what we would call a hole in that graph. And we'll talk about holes a little later on. We'll spend some time on holes, so I'm not going to spend too much time on it right now. But that would tell us that the function is continuous everywhere except at this point where x is equal to c for whatever reason. And we'll begin to discover what those reasons are a little later. We're discontinuous at that point, but that is called removable discontinuity. Okay, one thing I want to say before we get into this continuity test about discontinuous or discontinuity. If a function has infinite discontinuity or if it has jump discontinuity, we would then determine that that is actually it has non-removable discontinuities. Nothing we can do about it. It's just going to be discontinuous at that point. Now, getting on to this continuity test. We can be asked to determine and prove whether we've got continuity at a given point. And here we've got this given point is where x is equal to c. In other words, we're giving a value to x, and then we're trying to determine do we have continuity at that point or at that value of x. And so the first thing is does f of c, does it even exist? Okay, and if it does exist, then we continue on with our continuity test. And if not, then we know it's discontinuous. Now, we may have something that we're being asked to prove if it's discontinuous, but for right now, we're looking at identifying a point of continuity. And I'm on page 25 on our book, by the way. You may want to flip to that. Once we determine that f of c exists, then we're going to determine, okay, well, does this limit exist? And what that's really saying is as we get closer and closer to this value of x, as it's defined, as it's given to us, are our y values getting closer and closer and closer to the same value of y, or f of x, that we get at that point of c. And if they are getting closer and closer and closer, then we can determine that the limit is in fact true, where the limit is x is getting closer to c, that y, or f of x, is getting closer to that same value as it is as x is getting close to c. So here we go. We got a does it exist? This is number one. Does it exist? Second, are we getting closer from the left and the right? And then third, we can determine the limit or prove it. Okay, let's take a look at a couple of examples on the next couple of slides. Okay, so we're on page 25. We're looking at example 1. I'm down here at the bottom under guided practice. And I got a couple of screenshots here, but I'll touch on those for a moment. But if you look at that guided practice, it's asking us, is a function continuous when x is equal to 0? And this first one is where we've got f of x is equal to x cubed. Okay, so going up here, I have graphed this right here. And certainly it would appear that from the graph that x cubed, that when x is 0, there is a y value associated with that. In fact, 0 cubed is going to be 0. So it meets the first test. It checks the first test because it does, in fact, exist. Okay. Now, over here to the right here, we have a table of values. And so as I am coming from the left, if you will, from this direction, where x's are more and more negative, but I'm moving this way, so it's moving closer and closer towards this 0. I can see here from my table, when x is minus 3, y is minus 27. And I get a little bit closer to 0, where x is minus 2, well, y is minus 8. And then when x is minus 1, y is minus 1. And so I am actually getting closer to this value. Now, coming from the right, go in the opposite direction. Now I'm coming from this way. Am I getting closer and closer to 0? And we can see that I am. When x is 3, y is 27. When x is 2, y is 8. When x is 1, y is 1. And so we have now met this second test. Does the limit exist? Well, it would appear that the limit does, in fact, exist. Because we're getting, no matter which direction, whether we're coming from the left or whether we're coming from the right, we're getting closer to that 0. And so I can say that this graph is continuous at x equals 0. And when f of 0 equals 0, then the limit, I'm going to define this limit, like I said, I don't want us to get too bogged down on this, as x is approaching 0, then f of x is equal to 0. So as x is getting closer to 0, f of x or y is also getting closer to 0. All right, well, I'm still on page 25. I'm still in example 1. We're identifying a point of continuity. And I'm looking at guided practice 1B. And here you can see that I have entered both of the functions, the piecewise functions, into the graph, 1 over x, if x is less than 0, and just x if x is greater than or equal to 0. And that's going to give me a graph that looks like this. Now, what we got to focus on here is in this first equation, the blue. Maybe I should just actually put that in blue. Well, I don't have it in blue. We can see that it is coming along the x-axis moving towards 0, and then it begins to shoot down. And what we see right here is basically it's flatlined. Well, that doesn't even meet the parameter of our function, because at this point on our blue, x is greater than 0, so everything is just 0. This is kind of how this piecewise shows up. And then our other one, the portion of the graph that we're looking at, is this portion right here. Again, this is flatlined over here on y2. So when I come right here and it's asking me, is this continuous when x is equal to 0? Well, I go into my table right here, and I can see that when x is 0, well, it's an arrow. And so it does not exist. In other words, this is discontinuous. These graphs are discontinuous when x is equal to 0. And just to kind of continue on, I mean, right here, let's go on this part right here, is I am moving closer and closer from negative territory, closer to 0. I plug in the value of minus 0.999 and 0.099. Well, I can see that I'm moving further and further more. I'm getting more and more into negative territory. And that would support that my graph then here is looking like this. It's moving more and more into negative territory. And over here, as I am moving closer and closer to 0, okay, I am in fact actually moving. I'm coming from this direction right here. I'm coming down here from the right. Well, I'm getting closer and closer to 0. Okay, and even though I can hit it right here, well, on this y1, 1 over x, it doesn't exist. And so I can then say that this is discontinuous. Really didn't have to go any further than this, discontinuous. I'll just say discont. And as far as all the limit is concerned, as f of x, we could say as f of x approaches negative infinity. In other words, as y is approaching negative infinity, x is approaching 0. And that's as we're coming from the left. And as we're coming from the right, as x approaches 0 from the right, then we can just say that f of x is moving towards 0. All right, now I'm on the bottom of page 26. We're looking to identify the point of discontinuity. And in this guided practice 2A, right there in the bottom left-hand corner, it's asking us, it's giving us a function of 1 over x squared and asking us to determine, are we continuous or not when x is equal to 0. And you can see right here, I've graphed the function, 1 over x squared, and here is my graph. And I can see here that as I'm moving from negative infinity, I'm getting closer and closer to 0, but then I start moving upward. and also from coming from the right as I'm moving towards the y-axis, then I'm going to turn and I'm headed back up again. And from my table, I can see that when x is equal to 0, it does not exist. I am discontinuous at 0. And my table then proves as I'm moving along, again, this is corresponding moving from this direction, as I'm moving from negative infinity towards 0, I get closer and closer and closer to moving into this positive infinity territory. And on the other side, as I'm coming down the x-axis, coming from this direction, this will be represented going this way. I get closer and closer, but as I get there towards 0, I start now moving up towards positive infinity as well. But at 0, I am discontinuous, and no matter which way, coming from the left or the right, I'm still going to be discontinuous. So I've got infinite discontinuity, at 0. And so again, at the bottom of page 26, where we're looking at identifying a point of discontinuity, here you see I've got, this is example kind of practice 2b. I've graphed the piecewise function f of x plus, 5x plus 4 when x is greater than 2, and 2 minus x when x is less than or equal to 2. And so here, when f of x, we see here that we've got a jump from here to here as x gets right here at this 2. So we've got jump discontinuity. It jumps from one side to the other, and we can see here that if I'm coming here from the left, which would represent this direction, I'm getting closer and closer to 0. But when I hit 2, essentially, even though it shows 0, 0 here, there can't be a value there. And then as I am moving away from, I'm moving in this direction, coming closer and closer from the right, you can see that I'm getting closer and closer here to 14. So I've got a jump in continuity. So it's when x, this is what it was really asking us, when x is equal to 2, well, that does not exist. Does not exist. We have a jump in discontinuity. And we can say that it is discontinuous because as f of x approaches 0, as x is approaching 2 from the left, and 14 as x approaches 2 from the right, it has a jump in discontinuity, at f of x equals 2.